Okay, we have a block of mass M on a table. It's being pulled by a string of negligible mass. The string is parallel to the table, and the acceleration is A. We want to find the coefficient of kinetic friction between the block and the table. All right, so for our free body diagram, we have tension pulling to the right. We have a normal force acting up. We have gravity acting down. And then there's some friction. We don't know how much, holding things back. But the normal force and the force due to gravity should equal each other, since it's not falling through the table or floating up in the air. It's just being pulled sideways. And so that lets us know that the normal force is equal to the magnitude of gravity, which is mass, in this case capital M, times 9.8, which is G. So we're just going to leave things symbolically. So MA is the sum of all forces acting on, that's affecting the motion on the object. So that would be MA, the tension minus the force of friction. Well, force of friction is related to the normal force, where force of friction, in this case, is the kinetic friction, is mu times the normal force. So I want to drop that in. So we have MA equals T minus mu K. The normal force, we just said that is mg. So mg. So that's a mu, that's a m. I know mine looks similar, but we'll go with it. And we've got to solve for mu. So I'm going to move the t over. And so we get ma minus the tension equals negative mu mg. Let's get rid of the negative sign here. So that becomes t minus ma equals mu kmg. And then we're going to divide both sides by the mg. So we get mu k, which is the coefficient of kinetic friction, equals t minus ma divided by mg. So that would be the coefficient of kinetic friction. Let's take a look at another one that is a little bit more interesting. Okay, on this one we have another mass M being pulled across a horizontal table, but this time the rope makes an angle to the horizontal of theta. And we want to find the acceleration of the system. So we're looking for what A would be. So if we draw a free body diagram of this one, we have gravity acting down. We have the normal force acting up from the table. Tension is at that angle theta with the ground, and we do have friction going back the other way. Now, in this case, the normal force is not equal to the weight of the object, because we've got this other tension acting up, and that tension is doing a couple of things. Not only is it pulling the block across the table, but it is also lifting up on the block. So we have part of the force pulling across the table and part of that force actually lifting it. And so this part that's lifting it will be T sine theta. The part that's pulling across the table is tension cosine theta. So we had to break those up into components, and don't do that on the free body diagram. Do it separately. All right, so let's see what we've got here. Well, let's figure out the normal force. The normal force is usually equal to the weight of the object, but in this case, this force is picking up on it. So it's not having to hold up the entire weight of the block. It's only holding up a portion. So we're going to subtract off that part of the tension that's actually lifting the block. So that's our new normal force. And so since friction is mu times the normal force, we get that our normal force, or that our friction is mu k, because it's kinetic friction, Fg minus T sine theta, but Fg is just mass times gravity. So this becomes mu k mg minus T for tension sine of theta. All right, so we got a complicated friction term that we're looking at. Now let's get into actually moving it across the table. So for that, we have MA equals the sum of the forces that's actually affecting the motion. So in this case, we have MA, we're going to try to find that, equals the tension that's pulling it sideways, which is T cosine theta, minus friction, which is this mess right here, mu k mg minus T sine theta. And we're looking to find the acceleration. Well, at this point, we've got some help because we just have to divide through by the mass. So the acceleration in our system is going to be T cosine of theta minus mu k, which is the coefficient of static or kinetic friction, mg minus T sine of theta, with that whole thing divided by the mass of our block. Okay, so we got that figured out. Now, what happens if we're not on a horizontal table? Let's see what happens there. So in this case, we have a block at rest on an incline that makes an angle of theta to the horizontal. So I've got the free body diagram drawn. Now, the thing is, and where most people mess up, is let me redraw that free body diagram because I want to draw on this one. So we have weight acting down. We have friction acting up the incline because it's sliding down the incline. And then we have a normal force over here. And the friction and the normal force are going to be at right angles to each other. And the reason why I want to do that is because I want to go up to that drawing. And I want to break this weight vector into its components because we're going to have two components. We're going to have one component that's perpendicular to the table. And then we're going to have another component that's parallel to the table, or the ramp, I should say. That's parallel. The one perpendicular, and through the magic of geometry, this angle is the same as that one because they're similar triangles. So the perpendicular side, which is this side, is going to be Fg cosine of theta, and the parallel one is going to be Fg sine of theta. And we know that weight is mass times gravity. So I'm going to go ahead and substitute those in. So when I do, the perpendicular one becomes mg cosine theta, and the parallel one is mg sine of theta. All right, so we know what those are. I'm going to keep them over here because we'll need them later. While I'm at it, let's look at friction. So friction is equal to, in this case, it's at rest. So that's static friction, so that's mu s times the normal force. Now the normal force in this case is going to be equal to this force perpendicular. So we can take that term and plug it in here. So force due to friction is going to be mu s mg cosine theta. So that's our term for our friction. Now, since this is at rest, if we do ma equals the sum of the forces, well, A is going to be equal to 0 meters per second squared because it's stationary, it's not moving. Now, this will also work if the block is sliding down the ramp at a constant speed, but then it'll be kinetic friction here, not static friction. So the coefficient will change subscripts. But so this will be 0, and we have the component of the object's weight going down the ramp, so that's the force parallel, minus the force of friction. So I can substitute those in. So force parallel is mg sine theta minus this, which is our friction term, mu s mg cosine theta. I want to move this over. So mu s mg cosine theta equals mg sine theta. Now I want to solve for mu s. So I want to divide by the mg cosine theta. And we get a really interesting solution. So we get mg sine theta over mg cosine theta. And what happens is the mg's cancel each other out. So we get sine over cosine, which sine over cosine is tangent. So the coefficient of static friction will be equal to the tangent of theta. Same thing if it's sliding down at a constant speed, then the coefficient of kinetic friction will also be equal to tangent theta. Let's do one where it's not sitting still. All right, now we got a block M accelerating down an incline that makes an angle of theta to the horizontal. Coefficient of kinetic friction is mu k. What's the acceleration of the block? All right, just like last time, let's get a free body diagram drawn. We have the weight of the object going down. We have some type of friction going back up the incline since it's sliding down the ramp. And then we have a normal force perpendicular to the surface. Now I want to redraw it up here because I want to, again, do that components of the weight that are acting both parallel and perpendicular to the ramp. So we have one component, force perpendicular, that's acting that direction, and we got another one that's acting parallel to the surface. So we call it force parallel. This angle again is theta through the magic of similar triangles. So this becomes FG cosine theta, and the parallel side becomes FG sine of theta. And if we go ahead and substitute in our letters, because FG is equal to mg, we get mass of the object, or in this case the block, times gravity, times the cosine of theta. Parallel is mg sine theta. So again, I want to keep those because I'm going to use them later. Now then we talk about friction. The force of friction is equal to mu, k in this case since it's sliding, times the normal force. which the normal force in this case will be equal to the force perpendicular to the incline. They should have the same magnitude. So this becomes mu k capital mg cosine theta. That's the term for the frictional force that's acting on the block. Now to figure out the acceleration, we need to do ma is equal to the sum of the forces that's affecting the motion that's going into moving the object. So that's capital M. A we don't know, but what's making it slide down the ramp is this parallel component of gravity. So that's going to be mg sine theta minus the friction. There we go. That's the intermediate step. Minus the friction, which is mu k mg cosine theta. Now at this point, I want to do something to make my life a little bit easier. There's a mass in each term, so that mass can be canceled out. So the acceleration of this block down the ramp is g sine theta minus mu k g cosine theta. And that's the acceleration of the block sliding down the ramp. Let's do one where we're actually pushing the block up the ramp. See how that affects the solution. Okay, so we have a similar situation. We have weight acting down, the normal force perpendicular to the surface, and friction acting on it, as well as a push. In this case, let's just call it T. It could be a rope. I said somebody's pushing it. But if that's going up there, which direction is friction acting? Well, friction's always going to kind of oppose your main motion. So friction's actually going to be acting in this direction. So how does that affect everything? So let's take a look. So again, if I redraw it up here, there's my tension pulling the block up the ramp, normal force, and then a little bit of friction heading back the other direction to oppose what's going on. They still make right angles to each other, normal force and friction, but now it's kind of on the other side. We still do the components of gravity, the one perpendicular and the one parallel. So this one is mg cosine of theta, because again, through the magic of similar triangles, those two thetas are the same. And this one becomes mg sine theta, because that component of gravity is just mass times gravity. So we just substitute that in so I can save a little bit of room. But I will do this. Since I said our mass is capital M, force perpendicular is capital Mg cosine of theta, and the force parallel to the surface is capital Mg sine of theta. Friction is still going to behave the same way. So the force of friction is equal to mu, this is kinetic friction, times the normal force. And the normal force is going to be equal to the force perpendicular in this case. So we get mu k perpendicular is capital Mg cosine of theta. Remember, that's mu and that's m. So we got that term down. Now we have to put everything together and see how this force up is going to affect things. So we're going to do MA equals the sum of the forces. So I'm going to first write out all the forces. So that's MA equals that tension pulling up minus the coefficient, the friction, but also minus the component of the weight acting down the ramp. That's also going to slow things down some. So now when I put all these and substitute them in, we get MA equals our tension, whatever that happens to be, minus friction, which is mu K M G cosine theta, minus the force parallel, which is mg sine theta. And I actually want to find tension. So I want to take these two terms and move them over to the other side. So we get tension equals MA, and it's a capital A, minus mu K mg cosine theta minus plus when I move them over. Almost made a mistake there. Mg sine theta. I can make this a little bit prettier by pulling out the m's. Sine theta plus g sine theta. But that will be the solution to figure out the force up the ramp to get it to accelerate at A. All right, thank you for watching these algebraic solutions. May not have been fun, but hopefully it helped you out on whatever you need to do. Please like and subscribe and tune in for some more videos. Bye.